If we have length 10, we have at least one letter, at least one number, at least one special character from this group of 4 characters, then we need to figure out how many passwords we have. Yes? Are we assuming the password is case sensitive? Which one would you like to solve? No. Are they usually case sensitive? Yes. If I don't specify on a problem, you should write down your assumption that makes the problem easier. And I had a clever suggestion up here. Let's assume that our keyboard only has one letter that works. We're not going to do that. We're going to say there's 26 letters, there's going to be 10 numbers, and we have 4 of these special characters. Okay, now, how do we start to solve this problem? The biggest challenge in a counting problem is usually when we can have different numbers of things that are the same. Right? So order matters here, but we have replacement. So it's again, we might have replacement. We might not. So it's again an annoying problem. So we want to get rid of that. And one way to get rid of it is to decide exactly how many of each of these things we're going to have. And then solve that problem. And then do it for all the different ways of having exactly how many of each of those things. So let's assume that we have one letter, one number, and the rest are special characters. Now I'd like you to solve that problem. I'll give you a couple of minutes and just solve that one, and then we'll come back together. Okay, so let's talk about number 1 here. How many different ways are there to choose where the letter goes? 10. So I put my 10 numbers for positions in a hat, and then I choose out which one the letter goes in. And so remember that we always actually want to do an example, make something concrete. Try not to work in the abstract. So I'm just going to choose a place for my letter to go. And when I did that, there were combinations of 10 things taken one at a time, ways to do that. Right? Because the order didn't matter which one I chose. I threw them in a hat. I'm going to pull one out, and I'm going to say the letter goes there. Then I'm going to choose where the number goes. How many choices do I have left? 9. I'm going to just pick a place for the number. So the way for doing that was 9 things. I'm going to choose one of them. Now the rest of those are going to be special characters, right? And how many special characters are there? There are 4, so in all the blanks, I can choose any one of 4 things, right? So I've got 4 choices in each of those. Now, these were just the ways to pick this position, but once I pick the position, there's ways of putting stuff in there, right? So how many ways are there to choose letters? 26. So there's 26 in there. And how many numbers? There's 10 in there. So I have to multiply all these together because remember that all of the letters in the password must be present. So all the numbers that went in those blanks, I'm going to multiply together. So it's going to be 4 raised to the what? 4 raised to the 8 times 10 times 26. And all of that's going to be multiplied by C10(1) and C9(1), all multiplied together to give us this answer. So I separated the problem into phases. What I was going to do first, what I was going to do second, then, what was left. So the first thing I did was I chose where the letters went. That's an easy thing to do because I'm only looking at one thing at a time. I have 10 places. I'm going to choose exactly where exactly one letter goes. I'm not figuring out what the letter is yet. The next thing I did, I had 9 places left. I'm going to choose where the number goes. Easy problem. 9 places, choose one of them. By the way, what is C10(1)? It is 10. And what is C9(1)? It is 9. Okay, good. after I did that, I said, okay, everything else is a special character. There's 4 of those. So each of those I can figure out those 4. I knew that the letter place had 26 choices. I knew that the number place had 10 choices. That's how we did this problem. We have to separate it into phases of what we're doing. So this doesn't solve our whole problem, right? So we solved exactly a very small part of this problem. So what would be the next problem we would solve? What'd you say? What'd you say? The letter has already been, the places, so this particular place that I drew was one choice, but there were 10 other ways. So this already counts all the ways of placing the letters and all the ways of placing the numbers and the special characters. This is the answer for exactly one letter, exactly one number, and the rest special characters. So now I'm going to have to do exactly 2 numbers, or let's do 2 letters and 1 number, and then the rest special characters. Okay? Okay, so we're going to do 2 letters, 1 number, and the rest special characters. Now let's look at our formula for the prior problem. Our formula for the prior problem said, okay, from the 10 places I'm going to choose where to put the letters. And there are 2 of them, so I'm going to choose 2. Then I'm going to, from the remaining spots, I'm going to choose how many numbers I have. And then I'm going to tell how many ways there are to do the special characters. It's going to be 4 raised to the number of slots left, which is 7. And then it's going to be 10 raised to however many numbers I've got. There was 1. And then 26 raised to however many letters I have. So each one of the blanks has to have a number in it. So if you look up here, the powers add up to what? They add up to 10 because there are 10 blanks, and there has to be a number in every blank. So if it's a letter blank, it has 26. If it's a number blank, it has 10. And if it's a special character blank, it has 4. Now we need to do 1 letter, 2 numbers. I'm surprised I haven't heard any groaning yet. Okay, you're just being nice or something, yes? Okay, that's a good idea. So remember when we did truth tables, we had to write out all the possibilities. That's what we're doing. We're writing out all the possibilities of having at least 1 letter, at least 1 number, and the rest special characters, and at least 1 special character. So we had an idea at the front here. This is a pain in the butt, right? That doesn't mean you shouldn't do it. It means if you come up with a better idea, you should do that. But if you can't, this is what you have to do. Now, it's not that horrible, but it is a pain. So let's see what the other idea is. So we have an idea in the front. What was your name again, Nathan? Nathan had an idea. And he says, why don't we come up with all of the possibilities and then subtract off the things we don't want? So just like when we did the combinations and we chose the dividers where the dividers go, the other blanks had to have the items, or we could choose where the items go. So almost every counting problem has an opposite problem that might be easier to count. Okay, so we know that our password is length 10, and we have the total characters that we could have in any blank is 26 plus 10 plus 4, right? So any blank could have that many in it if I just make any password that uses that set of characters. So this is 1 blank, and I got 10 of them. So that's going to be 40, and there's going to be 10 of them, so I'm going to raise it to the 10th for the number of passwords of length 10 with this character set. Does everybody understand that? Okay, what kinds of things do we have to subtract off? So if we have all numbers, if we have all letters, all special characters, if we have letters and numbers only, right? And letters and special characters only. And if we have special characters and numbers only. Now this is a lot less than all the different ways of adding up the number of exact counts for each of those different things. So how many strings are there that are only numbers? 10 raised to the 10th, because each blank only now can have a number in it. So it has only 10 choices, and there's 10 of them. All letters is easy, 26 raised to the 10th. So there's 26 letters, 10 blanks, multiply 26 together 10 times. Okay, all special characters, that's 4 choices raised to the 10th. So we're going to subtract each of those. And these are distinct from these. So there's no string that is all numbers and all letters at the same time. So I don't have to worry about the inclusion-exclusion principle that says that I have to add back the intersection, because none of these have intersections, right? That's a really important thing in counting, is make sure that when you're subtracting things or adding things that they don't have intersections, or if they do, you have to count them and add them back in or subtract them back out, depending on what you've been doing. Okay, now letters and numbers, that means I've got 26 letters and 10 numbers, so that means all of my ways of doing that is 36 raised to the 10. Letters and special characters is going to be 30 to the 10. And special characters and numbers only is going to be 14 raised to the 10. So I'm going to subtract all of these, and we'll have our answer. 40 raised to the 10th minus 10 to the 10th minus 26 to the 10th minus 4 to the 10th minus 36 to the 10th, 30 to the 10th, and 14 to the 10th. That's still really, really large, right? Really a lot of passwords. Did you get it on your calculator?
Yeah, it's like
6 quadrillion. I don't even know how many zeros that is. So I don't actually care if you write this number down on anything. So remember that when we solve counting problems, Dr. Barnes does not care what the actual number is. She only cares about the formula. Yes?